All right, welcome back. So we're still in the chapter of traveling waves, and I'm going to continue. We started sound waves. We looked at the intensity and the intensity level. And remember we said that the power, P, was the energy per unit of time. But the energy given off by a source per unit of time depends, how much of that energy you will get depends on the area that's facing the source. And the area will depend on how far away you are from the source. And so we define intensity was I equals to the power divided by the area. And I mentioned that if here is a source and it's radiating in every direction, if you draw a sphere around it that encompasses everything, you will get all the energy. But that energy falls on a sphere of radius r, which means you're dividing all the power divided by the surface area of that sphere, which is 4 pi r squared. So if it's spherically symmetric in every direction, then you will get the intensity will be P over 4 pi r squared. This is true if it's spherical distribution. You have a source here and it's emitting radiation or radiating energy, whatever the energy may be. It could be radiation, sound, whatever, in every direction. Obviously I drew in 2 dimensions, but it's in every direction. Then we talked about the sound intensity level. It was given the letter beta, and it was equal to 10 decibels, 10 dB, so I just put a 10 here, times the log of the intensity that you have divided by some standard intensity. And that standard intensity is the lowest intensity that the ear can detect. And it turns out it is equal to just 10 to the minus 12. The units, of course, it's intensity, so it's power per unit of area. So the power is in watts divided by the area, which is square meters. Okay? So let's do an example. Suppose you turn on a blender. They're usually pretty loud. And let's say the intensity level beta is 83 decibels. Right? Let's say, suppose if beta is equal to 83 decibels, what is I? What is the intensity? What's I? Well, we use the definition. You got beta is 10 log I over I0. And so the left side is 83 equals to 10 log I over I0. And you divide both sides by 10, so you get 8.3 is equal to log I over I0. To be able to access what's inside the log, you need to get rid of the log. So the inverse of this log base 10 will be 10 to both sides. So 10 to the 8.3 will equal to 10 to the log will go away. The log goes away and you just get I over I0. And therefore I will be 10 to the power 8.3 times I0 times I0. But I0 is 10 to the minus 12. 10 to the minus 12. So you solve for I. Let me just look it up here. I have, it's approximately 2 times 10 to the minus 4. 2 times 10 to the minus 4 watts per square meter. Now the question is, if I double the intensity, let's say I bring 2 blenders and I turn them on. If you have 2 blenders, then they're radiating at twice the amount, twice the power, so you have twice the intensity, so it will be twice this, twice I, because power is that. But now what happens to beta? Will beta double? Will it be, instead of 83, will it be 166? The answer is no, because it's a logarithmic thing. So let's see what happens to beta. Let me call it beta prime, and let's see what it is when I double the intensity. So beta prime will be 10 times the log of the new intensity, let me call it I prime, divided by I0. So you have 10 log I prime, this new intensity is just twice the old intensity, so it would be twice I divided by I0. So this is 10 times. The log of a product is the sum of two logs, so it would be just the log of 2 plus the log of I over I0. If you remember, like this, if you have log x, y, it is log x plus log y. And similarly, if you have log x over y, it is equal to log x minus log y. Just properties of logs. And while I'm at it, log x to the n will be n times the log of x. Just, you can review it, it's in the back of the book, some properties of the logs. Anyways, so you have beta prime equal to 10 log 2 plus 10 log I over I0. But 10 log I over I0 is the old beta. So beta prime equal to the old beta, whatever it was, this is the old one, plus 10 log 2. So beta prime equal to beta plus 10 log 2. Let's do it in the calculator. 10 times the log. Do I have the log here? Yeah, I do have log 2, log base 10. It's about 3.01, so about 3. So 3. So it is 83 plus 3, which is 86 decibels. So beta, when you double the intensity, beta only increases by 3 decibels. That's all. And so if you quadruple the intensity, so that means you double and then double again, so it will only increase by 6 decibels if you quadruple. And so on and so forth. I mean, you could just plug it in, but usually there are some tricky questions in textbooks or tests. They say if you double this and quadruple that, what happens? And so just remember, if you double the number of things that are given off the sound, the intensity itself doubles. But this artificial intensity level, which we made up, it's a scale that made up. It's a logarithmic scale. That doesn't double because it depends on the log. Okay? So that was that. The next topic will be the Doppler effect. So if you have a source of sound, for example, let's say you're standing and an ambulance approaches you. As it's approaching you, you hear a higher frequency. The sound looks like a higher pitch, will be a higher frequency. And when it's going away from you, receding, you will hear a lower pitch. The frequency sounds lower. So that's the source of the sound coming towards you. You hear higher frequency, and when it's going away from you, you hear a lower frequency. Similarly, if the ambulance itself is just sitting there, and you're the one who's approaching it, so in that case, the source is stationary, not moving, and you're approaching the source, you hear a higher pitch, and when you're going away from the source, you hear a lower pitch. So in either case, when you're approaching the source or the source is approaching you, the frequency is higher. Now, how much higher? How does the new frequency depend on the old frequency and the speed of the source as it approaches you, or as you approach the source? And in the final case that we will do, it will be you're moving and the source is moving, so both moving source and moving observer. So let me just show you here. So the Doppler effect. So case 1, moving source, stationary, observer. So here's the source of sound. Here's the observer. The observer is not moving, right? Now what you have to understand is sound in air will travel at the speed of sound. Whether you're moving or not, it still travels at the speed of sound. Because why? Well, let's say you're moving and speaking. Now, as you speak, you're shaking the air molecules. The air molecules are at rest with respect to the ground. So they will have the same frequency. I'm sorry, not the same frequency. They will have, the sound will travel at the same speed. Okay? So the speed of sound will be the same. So here is the source. Let's say it's here right now. It emits sound. It emits sound at a certain frequency. Let's call it f0, and it will have a certain wavelength lambda. So it's here. Now it will emit a sound wave. I'm sorry. This is the source, and the source is moving to the right with the speed of the source, and it's emitting sound. And the sound has a certain wavelength, it has a certain frequency, so it will emit sound waves periodically. Every period, capital T, it will emit a wave. So it emits the first wave when it's here. By the time it tries to emit the second wave, this first one will be here. This wave front will be here. All right, it will be here. This is it emitted a pulse, and that front of the pulse will be here, and it's traveling at the speed of sound, and the distance it would have traveled this distance, and it is equal to the speed of sound, which I call v, v times the period t. All right, the speed of sound will be v. But let me double check whether the book uses v or vs for the speed of sound, and the speed of source will be vs. Let me just double check that. Okay, good. The book simply uses v for the speed of sound. That's a good thing. So now, by the time this pulse has traveled here, the ambulance or the car will be here. And that's when it will, because it's moving to the right, and now it emits the second pulse, which is here. Now, how far to the right did the car move? It moved this far. And how far is that? Well, it's the speed of the car, which is the speed of the source. This is the speed of the car or the ambulance, the source of the sound. So it's Vs times the period. So it emitted the first wave and it reached here. The second wave was emitted, but it was emitted from here because the car is here. So the wavelength is actually just this much. That's the wavelength. Let me call it lambda prime. Lambda prime. That's the wavelength. So the wavelength, lambda prime, will equal to, this is just the old wavelength, lambda. This is the old wavelength. If the car wasn't moving, it will emit the first pulse. The first pulse will be here, and then the second pulse will be emitted from here because the car or the ambulance is not moving. This will be the original wavelength. But because it's moving, it emitted the first one here. The first one came here. By the time the car has moved here, it emits the second pulse. So the distance from the first pulse and second pulse is only this much. And now if you wait one more period, this pulse will be here, and this pulse will be somewhere here, and the distance between them will still be this. So this is the new wavelength. And it will equal to v times t, which is the old wavelength, minus, right? I'm looking for this distance. So it's this whole distance minus this, minus Vs times t. But the new wavelength, this new wavelength, will equal to the speed of sound times the new frequency. This new wavelength will be the speed of sound times the new frequency. The speed of sound will still be the same. So it's equal to, you got lambda prime times f prime will equal to the speed of sound. Where f prime is the new wavelength that, lambda prime will be the new wavelength observed by the observer, and f prime will be also the new frequency that the observer hears. Okay, so I'm going to replace this by, so lambda prime will equal to v over f prime. So I have v over f prime will equal to v minus vs times capital T. But capital T is the period, and the period is equal to 1 over the frequency, the original frequency, the source frequency. So 1 over the frequency. So what we'll do is, you have, let me write it on the bottom here, 1 over F. And so let me just flip both sides, so we'll get F prime over V will equal to F over V minus Vs, okay, V minus Vs. And then I'm going to multiply both sides by V, and I will get F prime will equal to V times F divided by V minus Vs, V minus Vs. And the next cosmetic change we will do to it, we're really done. I'm going to just factor out the V, the speed of sound. So I get F prime equal to, when I factor a V, I would have Vf divided by V times 1 minus Vs divided by V. And so you get Vf prime equal to F over 1 minus V, the source, divided by the speed of sound. And this is it. This is when the source is approaching the observer. The observer will hear a frequency that is higher. Why is this higher? The speed of sound is 343 meters per second in air. A car or whatever, it would be moving at a speed, let's say 25 meters per second or something. So you'll have 1 minus a number. So this number here would be less than 1. When you divide by less than 1, you would have a larger number than 1. And so this number here, it would be, let's say, 2 or 1.75 times F. So F prime will be larger than F. That's when the observer is moving towards it. On the other hand, if the car is moving away, you will see that lambda, the wavelength, will be larger, and you will, if it's moving away, you can redo the same calculation, but you will have the plus sign. So we usually just put minus plus. And then you can figure out which one is moving toward or away by knowing that if you move toward, you try to increase the frequency, and you take the sign, you choose the sign that increases the frequency. So to increase the frequency, you're dividing by something, and you know if you make that thing less than 1, the frequency will be larger, and so you choose the minus sign. If you're going away, if the source is going away, then you choose the plus sign, because 1 plus something will be larger than 1. You will be dividing by a larger number than 1. Okay. Next will be, let's do case 2 here. I'm going to summarize them both in a moment. So case 2 will be stationary source. Now the ambulance will just sit there. Stationary source moving observer. Okay. For the observer, we'll give the observer velocity v initial, v0, vo for observer. Let me see whether I think they use vo. Yeah, I think so. So here is the source, S, and the source is emitting sound. Now the source is not moving. The observer is moving at some speed, the observer. The observer is moving towards these. Now these wave fronts are approaching the observer with the speed of sound, and the observer is also approaching them with speed v. So how quickly will the observer approach them? First of all, this distance here is lambda, right? It is lambda, and lambda is equal to, this is lambda, and we know that lambda times the frequency is equal to the speed of sound, right? Lambda times the frequency is equal to the speed of sound. So now, how frequently is the observer observing those fronts? It will be at a higher frequency. Instead of waiting for those fronts to get to the observer goes to them first. So instead of waiting for them, the observer will go to them, so the observer ends up observing them at a higher frequency. So So you can already tell that the frequency will be higher. Now, how much higher is it? That will depend on the speed of the observer. So let's analyze that. All right, so let's calculate that. All right. So now, from peak to peak, how long will it take for the observer to observe the first peak and then the second peak? Well, that would be the time it will take the observer to go from the first peak to the second peak. That's the period, the new period. It would be t prime. And remember, speed is distance over time, so time is distance over speed is distance over speed. So, let me see, speed is distance over time, so time is distance over speed. Yeah, it would be distance over speed. So it would be lambda, the distance from here to here, divided by the speed. The speed will be, the relative speed will be the observer plus v, the speed of the observer plus the speed of sound, and that equals to the new period, which is t prime. That's how long it will take to observe the first peak and then the second peak, or the second peak and then the third peak. The time between observing two peaks would be t prime, and it's equal to this. Imagine, I mean, if you have a train, let's say you have a train here, right? If you're the only one traveling, then the time it will take you to travel the distance from over one wagon will just be the distance from wagon to wagon, like the length of the wagon, it would be the speed, the length of the. Let me see here. It would be the length of the wagon divided by the speed. But if the wagons are also approaching you, then let's say the wagons are approaching, you're going toward the wagons at 10 miles an hour, they're coming towards you at 20 miles an hour, then the relative speed will be 30 miles an hour, and so you will go across wagons that much faster. So that's what I'm doing here. Okay. And I confused myself in saying that. So anyways, so that's what we have, all right? So that's the period, meaning the time it takes to observe one peak and then the next. And the period is 1 over the frequency, 1 over f prime. So let's rewrite this. That's all, we're pretty much done. So lambda f is v, therefore lambda is v over f. And so this is v divided by f. That's on top. Divided by, here I have v plus v0, I'm going to factor a v. So I get 1 plus v0 over v. I just factored the v from the denominator. And here I have 1 over f prime. And we want to solve for f prime, so I'm going to simply invert, or actually let me leave it for a moment. I will write this as v on top, and then the f on the bottom will come to the bottom, f, and then 1 plus v observer over v, just a little algebra here, over f prime, so we get a clean formula at the end. So v and v, so you just have the 1 on top, and invert everything. So you get f prime will equal to 1 plus v0 over v times f. That's that. So when the observer is moving, this 1 plus v over v0 comes on the numerator. When the source was moving, it came on the denominator. Now, if the observer is moving toward the source, you have the plus sign, because it's on the numerator, it would be 1 plus something times f, that makes the frequency larger, higher pitch. If the observer is moving away, then you would have the minus sign. Now, the final case will be the observer is moving and the source is moving, and so you will get f prime. If you just combine everything, it'll be 1 plus or minus. Here, I should put the minus also. If the observer is approaching the source, it would be plus. If the observer is moving away from the source, it would be minus, so it would be plus or minus. And then v observer over the speed of sound. And then on the bottom, we have 1, also plus or minus. V, now the source, divided by v, and then f. I've combined both of these formulas. The case where the observer and the source are moving. Now, to choose the plus or the minus sign, you have to think about it a little bit. So let me show you how you would do that. So let me just rewrite this formula. and give you the 4 cases that could happen. I would write this formula on the back. So we get this super formula. F prime will equal to 1 plus or minus V observer over the speed of sound divided by 1 plus or minus V source over the speed of sound times F. You see, if the observer is not moving, this is 0, and you will just have the source moving. If the source is not moving, you will have 0, and then 1 plus 0 is 1, and then you just have the observer moving. If both of them are moving, you have this larger formula. So you can have the following. Here is the source, and here is the observer. Let's say they could be moving towards each other. You can have the source moving to the right, and the observer moving away from the source. So the source chasing the observer. You can have the observer moving to the right, the source moving away from the observer. Actually, let's choose this one. The observer chasing the source. And then finally, you have the source going away from the observer and the observer going away from the source. As you can imagine, this will be the lowest possible frequency, and this will be the highest possible frequency. Source moves toward the observer, makes the frequency larger. Observer moves toward the source, that makes the frequency larger. And this is intermediate. This is the lowest. So what's F prime here? Which one should we use? The pluses or the minuses? Well, it would be this. F prime would be 1. I will leave the plus or minus here. V observer over over the speed of sound divided by 1, leave a blank, V source over V times F. Let's see if we can figure out what the sign should be. Let's see. The observer moves toward the source. The observer wants to make the frequency larger. The observer is in the numerator. Larger numerator means larger overall fraction, so plus. The source moves toward the observer, wants to make the frequency larger. So it's in the denominator. So smaller denominator means a larger fraction, so we need smaller, so subtract. For this one, you get F prime equals to 1, leave a blank, V over 1, leave a blank, V sound, or V source over V, like so. Now, the observer moves away. The observer is trying to make the frequency smaller. The observer is in the numerator. How do you make it smaller? By making a smaller numerator makes the own overall number smaller. The denominator, the source is moving toward the observer, so the source is trying to make the frequency larger. So it's in the denominator. Smaller denominator is a larger fraction, so subtract. So both are minus. The third case, you get F prime will equal to 1, leave a blank, leave a blank. So now, the observer is moving toward the source, right? So the observer is trying to make the frequency larger, so larger numerator means larger overall fraction. The source is moving away from the observer, so the source is trying to make the frequency smaller. A larger denominator means a smaller overall fraction, so add them. For this one, you get F prime is equal to, again, leave a blank, V observer over the speed of sound, over 1, the source divided by the speed of sound times F. The observer is moving away from the source. That means the observer is trying to make the frequency smaller. Smaller numerator, smaller overall fraction. The source moving away from the observer, so the source is trying to make the frequency smaller. Larger denominator makes the fraction smaller, so larger denominator, add. So these are the 4 possibilities that you might have, all right? And V here is the speed of sound. This V without anything, it is the speed of sound, and it is in air, it's 343 meters per second. Okay, that number there. The speed of the source and the observer will be given to you, okay? So let me check the timer here. Okay, still, well, it's about 30 minutes. So I will pause this one here, and then I will start in the next video and do an example or two on this.